welcome back. In the first part of this lecture, we introduced the concept of temperature as a way to measure the internal energy of an object using the absolute Kelvin scale, and then introduced Kirchhoff's laws of spectroscopy, which describe the origins of a continuous emission line and absorption line spectrum, and then turned to a description of a continuous blackbody spectrum arising from an object characterized by a single temperature T. We now turn to the other two types of spectra described by Kirchhoff's laws, emission and absorption spectra. Kirchhoff's second law states that a hot, low-density gas produces an emission line spectrum. One of these is shown here. We see in this spectrum bright emission lines from atoms making up the gas and darkness in between these lines. Light is emitted only at very specific wavelengths unique to the atoms and molecules in the gas. It was well known to chemists of the 19th century like Kirchhoff that gases of different types, when subjected, for example, heated in a flame or subjected to electric current, would produce a very different and very characteristic spectrum. But they didn't understand why this was the case. They also found, Kirchhoff's third law, that a continuous spectrum viewed through a cool gas would produce an absorption line spectrum. Here, the continuous spectrum is seen as the continuous rainbow wash of color, but the absorption spectrum are places where light is missing from the spectrum, where we see these dark lines crossing the spectrum where light has been absorbed. The light is absorbed only at very specific wavelengths that are unique to the atoms and molecules in the gas. However, not too surprisingly, these two emission and absorption spectra are closely related. The absorption lines from a cool gas are at exactly the same wavelengths as the emission lines from a hot gas of the same composition. For example, if you were to have a hot gas of hydrogen and take the spectrum, you would see the emission line spectrum arrayed across the bottom. But if you were to look at a cold gas of hydrogen, backlit by a continuum source, you would see the top spectrum. The continuous rainbow wash of colors is the backlighting continuous spectrum, and the black absorption lines would occur exactly corresponding to the locations we would see for the emission lines. Emission and absorption lines have their origin in the structure of atoms. While this was unknown to the chemists of the 19th century, understanding this was a major piece of figuring out the nature of the atom in the development of quantum mechanics in the early 20th century. The basic description I'm going to show here was due to Niels Bohr. We're not going to go into it in some detail, but just enough to give you an idea of how it works. Consider a single hydrogen atom. It's the simplest atom of all, consisting of a single proton in the nucleus orbited by a single electron. One of the important rules of quantum mechanics is that electrons can only exist in orbits of a particular energy. If you have either more or less of that energy, you're not going to be in that orbit. You can only be in an orbit with exactly the energy of that orbit. Small orbits, with the electron close to the nucleus, are of low energy, and big orbits, with the electron orbiting far from the nucleus, have a high energy. So here's a sketch of a hydrogen atom, and I've drawn in the first three orbits of the atom, numbered 1, 2, and 3. The laws of quantum mechanics say the electron can only be in orbit 1, like shown in the sketch, or orbit 2, or orbit 3. Consider the possibility of the atom being in a high orbit, perhaps up in orbit 3. An electron in this high orbit will want to try to make its way back down to the lowest orbit, called the ground state. It will do this by essentially falling from the high energy orbit to the low energy orbit. To do this, it must give up the difference in energy between the higher energy orbit above and the low energy below. Energy of 3 minus energy of 2 is the energy it has to give up. That energy is given up by emitting a single photon whose energy is given by the jump difference. This photon will have a fixed energy corresponding to a fixed wavelength. In the case of the electron in hydrogen jumping from the third to the second orbit, it will emit a single photon whose wavelength will be 656.3 nanometers. This is red light. If a jump was to be made, for example, from other levels, you would get different energy differences and therefore emit different energy photons with different wavelengths. If you look at an ensemble of atoms, not a single atom now, but billions upon billions of hydrogen atoms, all making different jumps between different levels, the combination of all the different allowed jumps from all the different atoms in the gas give you a very characteristic spectrum of multiple emission lines. This spectrum is characteristic and unique to that atom. Indeed, each and every chemical element has its own spectrum, and this spectrum is as unique to the atoms as a fingerprint is to human beings. We often say that we use the spectrum of atoms to fingerprint a gas. We can see, aha, this particular pattern of bright lines tells me that hydrogen is in the material. This particular pattern of emission lines says helium. This pattern of emission is a pattern of oxygen, or neon, or iron. They act like a fingerprint that identifies the atoms that are present in a gas. This is going to be extremely important to us because it is going to give us a way to know what the composition of a gas is. For example, in space, there are hot glowing gases in the form of hot nebulae. These are going to emit an emission line spectrum consisting of the emission lines from all the atoms present in the gas, and I can look at that spectrum and see that hydrogen, helium, oxygen, neon, and so forth are present in that nebula. The sun's spectrum is approximately a black body with a temperature of 5,770 degrees Kelvin. Deviations from this black body, however, are apparent. The black line here plots the sun's spectrum from the ultraviolet way out into the infrared, and this faint green line plots a black body spectrum for a black body of temperature 5,770 degrees Kelvin. If you look at this, it looks that it doesn't match very well. In some places, the spectrum of the sun is emitting more light than the black body. In other places, the black body is emitting more light than the sun. For example, down here in the ultraviolet and out here in the visible to near infrared. What's happening is that we're seeing deviations from a pure black body that are due to atomic and molecular absorption occurring in the sun's atmosphere. If you added up all the light underneath the black curve, you would get the same area, the same total energy as the area underneath the green curve. That's why we say that stars like the sun are approximately black bodies with a single temperature. That temperature is characterized by the last transparent layer at the very top of the sun, below which it becomes opaque and we can't see in. This gives us a way of estimating the temperature of a star by looking at seeing what part of that continuous spectrum component appears like a black body. However, superimposed on top of that black body are thousands, maybe even millions of absorption lines. This is the sun's spectrum in which we've now removed the black body component and are showing just the deviations from the black body due to absorption in the atmosphere of the sun. There are thousands of lines in this picture. We've taken what should have been one continuous rainbow wash of color, snipped it into pieces, and stacked them on top of each other so we can see them. If I didn't do this, this spectrum would extend for tens of feet in either direction. We see a number of bright lines. For example, that red line of hydrogen is this absorption line right here. Down here, this group of three relatively prominent lines turn out to be absorption from magnesium. This is another line of hydrogen. These two are lines of sodium. And many of the lines that we see here are in fact due to iron. By comparing the different absorption lines that appear in a star spectrum with the spectrum that we take in the laboratory of pure elemental samples, we can use that information to tell which elements are present in a distant star or a nebula. For example, here's the spectrum of the sun now, shown in a compressed form. On top is the spectrum in emission of sodium. This is a sodium gas flame spectrum. And we see, for example, that this dark absorption line in the sun here in yellow light corresponds exactly to this sodium line here. Similarly, calcium lines in the spectrum have an exact correspondence with calcium lines in a pure spectrum here. So we can identify lines of calcium, lines of sodium, and so on and so forth. We could tell which elements are present, However, telling how much of each element in what proportions is present is a lot more complicated problem, but it can be done. It's a problem that's well beyond the scope of this course, but understand that if you see the presence of an element in the spectrum of the sun or a star or a galaxy, then in principle, with a little bit of work in quantum mechanics, you can work out what proportions of each element are inside the star or galaxy that you're looking at. Therefore, spectra are exceedingly powerful. They give us a way not only to tell what it is we're looking at. If I saw just a continuous blackbody spectrum, I would know I'm looking at a hot solid. If I saw just an emission line spectrum, I would think I was looking at just a hot thin gas. But if I see an absorption line spectrum against a hot continuum, I know that I'm looking at a cooler atmosphere on top of a hot continuum. By looking at the combination of emission or absorption lines in the object when present, allows me to tell the chemical composition of the object. Spectra are an enormously powerful tool in astronomy. They allow us to learn a great deal about the object's temperature, its elemental composition, indeed, even its pressure, and many, many other characteristics.